Hey guys, so we're now in the second unit of what we're going to talk about. So we're done with optics and we're going to talk about thermodynamics and temperature. And I suspect you guys have mostly all had a chemistry class at some point in your life. So we'll go quickly through the stuff that we can go quickly through. But I do want to set up a little bit of explanation about why some of our units, which are funny when we talk about temperature, exist, and a little bit of historical context about this whole problem. So actually, if you go back to the time of Newton, the question wasn't what is heat, it was actually what is cold. Imagine that you live in 1650 in England, and the way that you perceive the world is really like, it's a cold night, and you almost feel as if there's this insidious fluid kind of permeating your body as you get cold and robs you of your life force. So people actually thought that the thermodynamic question was not what is heat, but what is cold. And then one cold evening, Robert Boyle, the chemist, now known as a chemist, decided to figure out how much cold weighed. So he took a big barrel and he filled it with water and he weighed the water, and then he put it outside overnight and it froze. He brought it back in and he weighed it, and he realized that it weighs the exact same. And then subsequently, people figured out what you now know is that cold isn't really a thing. Cold is the absence of heat, and what heat is the thermal agitation of molecules. So temperature, in some sense, is a measurement of the average kinetic energy of wiggling atoms and molecules. So that's the modern scientific inquest into this. Working completely independently from these highfalutin natural philosophers, there were the bakers and the brewers and the people who made wine and cheese. And what they had developed is a kind of empirical way and a set of tools of describing this, and they did it in Italy and in Europe and in Germany independently. So there are these funny different scales that we use, and they came up with these instruments to measure degrees of heat or temperature. So the two famous ones that you start with when you're learning about this in either Europe or honestly just the US for Fahrenheit are Fahrenheit and Celsius. And there's an interesting thing that shows up. Their formulas to convert in between the two of them. Eventually we'll come up with absolute. But the interesting question in some sense is you can relate these with linear transformation. So they're related by a line. There's no complicated squaring or logging that you may have seen when you've gone from one set of units to another. So that has two consequences. One is that if you want to convert from a temperature scale to another, all you have to do is find two landmarks. And the two landmarks that people usually use is if you take some water, pure water, at the surface of Earth under standard pressure, and you freeze it, that happens at 0 degrees Celsius. So the degree marker is for Celsius and Fahrenheit, not for Kelvin. We'll talk about that when we need to. And that also freezes at 32 degrees Fahrenheit. Likewise, if you want to boil water, you would do that at 100 degrees Celsius and 212 degrees Fahrenheit. Okay, so there's another landmark, and I just want to point this, really should be like here. I want to point this out for maybe kind of like quirky historical reasons, is that maybe you think that Mr. Fahrenheit got this wrong, and a landmark that people were using was the body temperature of a healthy human. That's at least a degree or different, maybe 2 degrees off. 100 Fahrenheit actually doesn't have anything to do with human physiology. It's the rectal temperature of a cow. I presume, or I hope, that's because Mr. Fahrenheit was a vet. It's not human temperature. What a weird way to anchor your scale, but that's what it is. Okay, so let's say that we want to convert in between these two things. We have our two landmarks, and the second interesting point to make is that why are they linear? So we'll get to that when we talk about thermal expansion. So I can take these two landmarks and I can come up with C is degrees Celsius, F is degrees Fahrenheit, and if I want to convert back and forth in between them, degrees Celsius, there's a nice round number, 9/5, F minus 32 with units. So that's the units, maybe slightly clumsy notation. That's the degrees Fahrenheit, subtract 32F. And likewise, we can invert that 9/5 degrees Celsius. And then what we need to do is add the 32 degrees Fahrenheit. Okay. Yeah, we'll take 1 second, just make sure that you're doing this properly. Let's just see what the average temperature of a human is in Celsius. So not 100 degrees. And again, some people run hot, some people run cold, but we'll just say normal. In Celsius. So I know that that's 98.6 degrees F, and I want to convert that to C. So the first thing I do is I subtract off, change the 0. So you think about this as an application of, they're linear, mx plus b. Subtract 32 degrees F, multiply by 5/9, and you get almost on the dot 37 degrees Celsius. So, not groundbreakingly difficult, but the point here is the units and the way that we write this, and then the fact that they're all linear, which again is a little bit of intriguing phenomenon. Okay, so something else happens, and I don't think this was really thought of in like pure mathematical terms at the time, of course, but it's been enshrined in thermodynamics as the 0th law of thermodynamics, and that's the idea of thermal equilibrium. And what that means about the molecules is something we'll get into. But the 0th law of thermodynamics, let's just kind of take like 3 blocks. So I have 1 block at TA, and then 1 block at TB. And what's true is that TA equals TB. So they have the same temperature. And then I perform a second experiment where I take TB and realize that it's at the same temperature as TC. Then I can deduce that TA also equals TC. This is something that might seem obvious, but it actually is kind of a big deal. So the idea that you have natural laws and phenomena that are equilibriate or transitive, if you want to think about it as a math thing, like A equals B, B equals C implies A equals C, this is how the world works in a measurement standpoint. So there are these really fancy machines in Gaithersburg, Maryland at the National Institute of Standards and Technology. And you calibrate your thing to that, and then you can take that thing out into the world and calibrate other things. So you don't always have to come back to the same reference standard. So what this means in a practical point is that we'll define what's called thermal equilibrium, and we'll say 2 things are in thermal equilibrium if their temperatures are equal. So what the 0th law really says is that if A is in equilibrium with B and B is in equilibrium with C, then A is in equilibrium with C. So it would say A in equilibrium with B, and then B in equilibrium with C, therefore A is in equilibrium with B. And already I'm using the shorthand that we're in thermo. When I say equilibrium, I mean thermal equilibrium, not mechanical equilibrium, which means all the forces balance. So A in equilibrium with B, B in equilibrium with C. Implies A is in equilibrium with C. And again, if you're a math person, you would just say that that's like a transitive law. Okay, so the second interesting point is that why are these all linear? So I don't need any sort of like, a second order polynomial or a logarithmic scale. Lots of stuff's logarithmic. When you turn your speaker volumes from 1 to 10, which I encourage you guys to do in this moment in time, is you're actually not increasing the intensity by a factor of 10. You're increasing it by, of 10,000 or something like that. So that's a logarithmic scale. So the reason for that is that we defined temperature through a phenomenon called thermal expansion. And again, this wasn't the eggheads like Robert Boyle and Newton. This was people who were doing something useful, like making sure that the bread that they baked or the beer that they brewed was uniform in quality. And the way that they did that is they realized that you could take a thin glass tube and you could put something like alcohol or later mercury. And what happened as the thing heated up is that this thing would rise in a linear fashion. So what's true is if this delta T was 2 degrees, we'll just say Celsius, and it corresponded to, 5 millimeters, then this delta T, if that was 2 degrees Celsius, that would be the same delta L and the same delta L. So what thermal expansion was empirically noticed to be was linear. So double the delta T, you double the delta L. And this will be our first meaningful formula when we talk about thermodynamics, because you guys know about Fahrenheit and Celsius, I presume. And I also encourage you to look at some of the pictures, I'll post them, of these beautiful Venetian glass thermometers. So huge coefficient of thermal expansion. So these things needed to be created in this bizarre and elaborate way where they would wind around, and they're actually pretty gorgeous. And they have these hand-painted degree markings because this was actually full of alcohol. Okay, so what we know is delta L, and I'll use little l because I think your book does, is proportional to delta T. So now what we have to do is fill in the details. One thing to notice is that if I have a short bar and a long bar and heat them up, so I heat them up by the same amount, so we'll call it 20 degrees or something like that. So what I'm going to get is a little bit of delta L. So this is what we're talking about, the increase in length if we increase this by some temperature delta T. So what do you think is going to happen, call it 5 degrees. I heat these two bars up by 5 degrees. What's going to happen to this bar? Is it going to be the same delta L or longer? So you probably guess longer. The more molecules you have, the harder you wiggle them, the greater the length increase you write. So really what's going on is that this should be interpreted as a fraction. And the first addition we need to make before we turn this into a full-on formula is to note that really what's going on is we're increasing delta L over L naught, the fractional increase. And then at that point, it's just realizing that there's a constant, somewhat annoyingly because alpha is also used to mean proportional. This alpha is the constant of thermodynamic or thermal expansion, but this is increase in length as a function of temperature. Double delta T, double delta L, but we have to do two things. One is remark that it's linear. People did that a long time ago. And secondly, realize that if you have twice the length of bar, you'll have twice the length of extra bar after you thermally expand. So this is it. This is what's called the coefficient of linear expansion, the alpha. And likewise, you could do this with area and you could do this with volume. We'll skip area and we'll talk a little bit about volume. And you notice this, actually. If you've ever seen the expansion joint on a bridge, it's precisely because this is a real phenomenon. So it's a great name for a constant, a coefficient of linear thermal expansion or linear expansion. Because it tells you exactly what it is. So every time we introduce a new formula, we got to introduce units. the units would be the units of the temperature that you're actually looking at. And something really nice happens here. You probably spent all of mechanics getting beat up about SI units, SI units, SI units. So if you measure this in centimeters and centimeters, they vanish. If you measure this in inches and inches, which is really sick, they vanish. If you measure it in meters and meters, they vanish. So that fraction means that the left-hand side is unitless, because we're dividing like with like. So really all you have to do is make the right-hand side unitless. Usually what happens, not sure if you're familiar with this notation, this means units of, has got to be whatever the reciprocal of those units are. So this might be 1 over degrees Celsius, or 1 over degrees Fahrenheit, or 1 over degrees, just kind of looking forward a little bit, 1 over degrees Kelvin. When we get to Kelvin, I'll show you that basically you're free of worrying too much about it, because 4 degrees change Kelvin is 4 degrees change Celsius. Okay, so in a picture and an example, I might have something like this. So let's say I have a copper bar. It's got an initial length L naught, and then heat it up. And what I have is L naught plus delta L. And I would find that by this formula. So the question is, what are these? Well, you could do a lab, and in other quarters you would do a lab, that determines this experimentally. I'll put it up for copper, and we'll do an example problem, and you'll be like, oh man, that's a small number. That looked like a really painstaking lab that I'm glad I missed, and you might be right. So just as an example, the coefficient, let's take 10 meters. And as you're about to see, my sig figs are an absolute disaster. So probably what I should do is write 10.0000 or something like that. But we'll leave it for a second. So what is it that I need to know to compute this? I need to know the coefficient of linear expansion for copper. So it turns out that a copper is 1.7 times 10 to the minus 6th, 1 over degrees Celsius. And then the rest is just kind of plugging in and going to town. So I have delta L, the thing I want, over L naught is alpha delta T. And everything's given to me, right? So I heat it up. So that's the change. I didn't know what temperature it was originally. All I know is that I heated it up by 20 degrees. So that means delta L is 10 meters needs many more sig figs, and you'll see why. But just pretend they're there for the moment. Alpha, and then 20 degrees Celsius. Units cancel out. Unitless, they're gone. And math happens, and delta L is, I've got to actually look that up. .4 times 10 to the minus 4. Because we multiplied by meters, we're going to get out meters. So that's about 1/3 of a millimeter. Okay. Which means, 20 degrees Celsius is the difference in between a cold morning time or something like that, a day where there's a difference. You have this bar that's about, the 10 meters is quite a bit, length of this classroom, for instance. Over the course of the day, it'll change by 1/3 of a millimeter. So this really isn't a profound effect. The expansion joints on a bridge only exist because the bridge is really big. And we'll do some more substantive examples. Okay, so this works for length, and that was just a warm-up. So maybe what we care about is volume. Leave this up for a second. While I'm erasing this, think really hard and write the equivalent formula for volume would be, and I'm pretty sure you're right. The only thing that might be tricky is, would this have the same units or not? Or sorry, the same exact constant or not? And it turns out no, there's a different constant. Volume would be a different constant. Turns out that there's a rule of thumb that this constant, volumetric expansion constant, is about 3 times bigger than that. It kind of comes from some geometry, and I'll sketch what that geometry might be. So this is the formula for volume expansion, and beta is, take a wild guess, you're right. Except maybe you didn't quite get the part of speech where you turned a noun into a verb or an adjective correctly. So volumetric means pertaining to volume. So let's just problem, and then I'll explain the rule of thumb that beta is about 3 alpha. And kind of culture of writing these units. Micro, so times 10 to the minus 6, even if there's, you know, not a ones place out in front. That's just the way it is. So we'll say how. So let's take hot water. So this would be, you know, kind of hot to the touch, and get it cool. So take a 2 centimeter on a side cube of water, and then just basically, you know, refrigerate it out over a normal-ish range of temperatures. And this is 2 cm on a side. So for that, I would need to figure out the volume, and then basically use the exact same sort of formula. So I have, and I'll do this in SI because SI never steers you wrong. You can get in trouble with other things. So let's say that I have 0.02 meters on a side. Volume would be that cubed. So that's 2 times 10 to the 2 times 10 to the 4 times 10 to the 6th. So that's 2 times 10 to the minus 6 meters is the volume, the initial volume. And then we're going to refrigerate it. So we hadn't talked about this yet, but we got to make sure that the SIGN sign is in correctly. So I have delta V over V, beta delta T. Okay, so I'm going to do 2 things. One thing, I'm just going to parse this and make sure that I get the sign right, just kind of from principles, instead of saying, oh, well, you know it's negative. Sorry, delta V is what we want. Sorry, that's meters cubed. So change is final minus initial as always. So we'll do that manually in detail. So the final is 10 degrees Celsius, the initial was 40 degrees Celsius, and we get the minus sign we were looking for. So basically, this thing is going to shrink, and we want it to shrink. So I have delta V over 2 times 10 to the minus 6 meters cubed, and then 210 times 10 to the minus 6th, 1 over Celsius, Celsius, I'll just leave off the units, because it's going to be unitless, minus 30. Okay, multiply by that. Already you're going to see this like astonishingly small number, right? Delta V, if you just look at this, it's, minus 6 times minus 6, so freakishly small number. And is minus 1.26 times 10 to the minus 8th meters cubed. Awful. So let's say I wanted to maybe turn this into more reasonable units. I could ask how far on a side it expands. So that would be an extension to make this, problem yield something that's more sensible to us. So I'll take the cube root of that, and that would be delta L. So and now we're talking about 0.002, and 1 sig fig is good enough. So shrinks by a millimeter. Okay. Great. There's a rule of thumb that's associated with this, and I got that cube picture up, so that's perfect illustration. That if you're ever at a loss, you know beta, but you don't know alpha for the exact same material. Different materials have personal alpha and beta, and you got to look it up from material to material. But there is a rule of thumb that's pretty nice. Is that beta is about equal to 3 alpha. And the derivation, as it were, the real derivation, a little bit of calculus goes a long way in this case, is that, let's say that I expand this. And I just kind of anchor the corner. So this is my cold cube, and then this is my warm cube. It's going to expand in that direction, it's going to expand in that direction, and it's going to expand in that direction. And roughly speaking, I have 1 in the x direction, 1 in the y direction, and then a little bit harder to draw 1 in, well, that might be the y direction, yeah, and then 1 in the z direction. 1 delta L, and then another delta L, 1 for each direction. So basically, a volumetric expansion is 3 linear expansions. So you can do a little bit more care with that if you do a calculus kind of argument. So last thing to say is that the warning on this is so these formulas, these linear expansion formulas, if you try to apply this to a gas, just the wheels are going to fall off the bus. We have this entire other way of figuring out what the volume of a gas is, and that's the ideal gas law. So this is for solids and liquids only. So this is something you might imagine is a little bit hard to demo, the idea of thermal expansion. So I have not a 10-meter long copper bar, and you can imagine if I heated this up over the course of a day, it might be millionths of a centimeter across. So there is one thing that is a very obvious example of thermal expansion, and actually is the basis of a pretty useful device, but you still need like a fair amount of heat to illustrate it. So here's a piece of metal, or so I say, and I'm gonna blowtorch it. And how bizarre, it seems to go the opposite direction as you think. So I'll let it cool down a bit, and then we'll turn it over, and maybe this has some weird affinity to flame and goes towards the fire, but it turns out that's not true. So what on earth is going on with this? So this is a bimetallic strip. So the two different sides of it are actually two different metals, and they're sandwiched together. And if you've ever seen one of those old school thermometers with a kind of analog hand on it, that's a bimetallic based thermometer. So I have metal 1, or metal A, and then I have metal B, the second one. Just make sure I'm not setting stuff on fire. And each one of these has their own personal alpha. So when I heat it up, what happens is one expands more than the other one, and it causes the thing to curl over in whatever direction is of the bigger alpha, right? So the more expansion per degree Celsius or Fahrenheit, whatever you choose to use. So the thing that you might see this in is a patio thermometer that, depending on where you live, might be like 60, 70, 80 degrees Fahrenheit. And then the needle points at that. Thermostats as well. So this is a wound coil of bimetallic strip, calibrated so that it uses exactly that phenomenon. So I'm not going to demo them because they're, it just seems like a bad magic trick. The other classical demo is you have these two things. These are both copper spheres, and you can fit one inside the other, or a copper sphere and a copper ring. Then I can thermally expand this, and it won't fit on the way back out. So this is a real phenomenon, and even though it's subtle, it is useful and practicable.